Okay, thank you. So very quickly, so this is going to be the course program. There's going to be 2 presentations made by Jean Casaer and Marcus Rowcliffe, which I also want to thank for the availability. Each presentation is going to last about 1 hour, and then there's going to be about 30 minutes time for questions, and there's going to be a coffee break in between. So very quickly, as you know, the report about the 2023 activities has just been completed and is now being revised by EFSA. This clearly is extremely important for us, as it is an important achievement. It highlights the efforts that we all have been doing and the growth of the network as well. As you can see here from this provisional map about the 2024 study sites distribution, the network has been growing quite a lot, and in both in numbers and in distribution of the study sites. And some sites are still missing from this map. Also, from the report, we had evidences of improved precision, and we believe some of these improvements are related to a better protocol implementation. So we'll keep highlighting the importance of following step by step the protocol. So this is why training sessions like this one are extremely important, and it is fundamental that all the processes explained here are followed thoroughly. Some small issues, criticalities that we have been facing during the report activities, which I'm just mentioning here. Then there's going to be other moments to go through these and to fix these things. But in some cases, we had incomplete information, either about results or study size information or about the protocol implementation. In some cases, we realized that the protocol was not followed thoroughly. So as I already mentioned, this is crucial. And in some other cases, we were missing the shape files of the study sites, which is extremely important for us to have a better understanding of how things have been done in each study site. Then there's going to be a few news that in the upcoming weeks and months we're going to share with you. So a new reporting method for the results to be shared with us. So we're no longer going to be using the shared Excel file that we used in the last years. And also we are going to incorporate further variables into about the study site, which are going to allow us to have a better set of information that can then be used for analysis and for the production of scientific papers. This is also something that we consider as extremely important and that we are going to tackle in the next few months, and that we are going to, of course, share with you and keep you updated and involved in. Finally, the assistance about the EOW. We want to highlight that, despite other people being involved, like the lecturers of today, they are not the ones you should be contacting for help or assistance. So for any general issue, doubts, questions, I am the person you should contact. So I'm sure most of you by now have my email, but I also reported it here once again. And in order to allow me to have to give you the best possible assistance, it would be great for me to have access to your Agouti project. So for those who didn't do that yet, or for the new project, it would be great if you could share with me the link to request access to your project. Finally, for specifically Agouti related issues, the contact is the Agouti team, of course, and this is the email you can contact them at.
Okay, thank you. Can you see my screen also?
Yes.
To interrupt, I
would just like to let everybody know that we are going to record the meeting for those participants that are not connected today. So if nobody has problems with that, we're going to record it. Thank you.
Okay. Okay, so good morning from my side also. I was intending to use the same slides we used 2 years ago, but then I discovered that we made so many changes and so much progress in Agouti that it would be useless. So I'm going to try to take you all live through an Agouti session. So maybe it would be good to shut down the videos, because otherwise I have to do a live connection with Agouti and a live connection with many of you on video, which could be the end of the internet. What are we going to talk about? We're going to talk about, oops, you still there?
I was still here.
Okay.
Yes.
Because now I see a completely different screen. We're going to talk about the import of data. How do we annotate images, use the artificial intelligence, and about the export. So now I'm going to go to Agouti. So this is the Agouti starting screen. And the first thing to do is to log in, of course. And once you log in, you go to the projects, and everybody has a project, and the one I'm going to play with is Vlaanderen test. So the first thing we would like to do when we come back from the field is to make a new deployment. So we go to add deployment, you select the site, you select the files you need, and it's very easy. You simply go, it should be very easy if my Google Drive was synchronized. Now it's going to synchronize. Otherwise I don't have images. I simply go to the place where I know my images are. It's one of the reasons why we stock them also as good as possible, really nicely. And so to get them into Agouti, you simply can do all. You say select all, but I'm not going to say select all. It takes too much time. You simply select the images you're interested in. I'm going to take less. There we go. And so he starts uploading the files. Can take some time. So maybe in the meantime, so you see saying I'm uploading 132 files. I already successfully uploaded 66, so he's counting. The number of duplicates is because it could be that if I have 3,000 images, I first select the first 1,000, and then I would like to select the second 1,000, but it could be that there is an overlap. So in that case, he makes sure and he checks. So 100% of all, everything is done well. No files any left to upload. 132 were uploaded. There are no duplicates, and there were no failed ones. Do I need to add something more before you can say, save the deployment? Best thing to do, text is not important. Well, is important for us quite often is the camera height. Should be at 50 centimeters. It's heading north. Depending on, but normally it should be flat. We don't use any bait. I'm not going to send it over there. So that looks all okay. Sampling point is added. I will add that one again. So there we are. And now we can add the deployment. So if I go, so now he's working on it. I will put it that way. So if I go to the list of deployments now, I added the deployment. I'm going to look for the 117. So what he's saying is there on the bottom is he's now creating the sequences. So what Agouti is doing now is looking at the images, and the settings are of our Reconyx cameras that it makes a photo burst of 10 pictures, and if there's still an animal, then it's triggered again, and he makes another photo burst of 100 pictures. So he's making long sequences, and as long as there are no 2 minutes between two triggers, the last one of the first one and this first one of the second one, he creates a sequence. So while he's doing this, and when he's finished with creating sequences, we get this image saying this is the location, there's a start date and an end date, which is looking at the images, the first image and the last image, which is uploaded. And now we can start annotating. There are two options. One is to have them annotated by the artificial intelligence, which you define in the settings of your program. And this one is no longer valid. So I should go and look for Europe version 5 is the latest one we're using. If I go back to my deployments, on location 117. So, okay, he also is ready over there, which is okay. So let's see, upload it again. So the one I just uploaded, he created the sequences. I can start to annotate. I can have the computer annotating, or I can ask, I can assign it to one of the collaborators to look at exactly this one. If I go into the annotation screen, there we are. I can go to the first one, and the first one is a very classical one where I see someone working, which is because we were putting up the camera at that moment. So there I said this is a setup pickup. So I can go to the next one. He's still waiting. He's still in there. And I can go to the next unannotated one. So he jumps to the next one, which is not yet annotated. And if I'm looking at these images, there's an animal down here. And there comes the second one. I hope you can see it. Those are small wild boars getting through. There you are. Again, the big one. So I have an animal that I'm sure of. The species will be a wild boar. There are at least 2 of them. The age, the juveniles, the sex, I really don't know. I don't know the individuals. I could say they were running, but normally we don't look at it. And I save it. So now I have 2 wild boar infant unknown that were saved in this sequence. If I go back 1, this is not another one. Okay, this is a good second example. So in this sequence, I have a female roe deer, and then a certain moment, as you can see, the sequence contains 20 images, so it's 2 triggers. And then at a certain moment, I see that there is a fawn. So I have 1 roe deer adult female, but I'm going to add, and this is nice in Agouti at the moment, the species you already annotated or you already observed, they appear down here at the bottom. So I can say, I would like to add an observation of another roe deer, which is a juvenile. I don't know the sex. Save. So now in this sequence, I have 1 adult female and I have 1 unknown juvenile. The reason why there are 2 observations and not simply one observation of 2 roe deer, if I know it, is that if afterwards, for example, I would like to do an analysis to see when I see infant roe deer, in the field, I can make a selection on only those species, also in further analysis. So finally, I'm at the finish annotating. I've done all the sequences in this deployment. So if I go back to deployments and I reselect the 117, I now see that this is saying 100% is annotated, which means all the sequences that are contained in this deployment are now annotated. If I drop this one, the one on the top only partly is done. This one also only partly is done. So a lot is depending on how you work within the team. We have in the team people don't annotate what they don't know, so specialists or other ones can have a look and continue to annotate whatever still has to be annotated. So there I have a list of, and there is a small, how do you call it? Small square over there, which allows you to say those who are 100%, I don't want to see them anymore, which makes that the list of deployments only is those where I still have to do something, or they still need files, no files were uploaded, or they still need to be annotated because they're not yet fully finished. So those are the two. If I unclick this one, I get again all the ones, but I get also a lot of 100% where no work has to be done anymore. So it's quite useless to have them over there. So that's step one. I have been annotating images based on the sequences which are available. If I look at the observations now, I get a whole bunch of possibilities to select, going from the sampling point. I will take 117 again. So those are all the animals, the species, scientifically, and on English name. Is it a species that I've been seeing, or is it a pickup setup or whatever? I only want to see the adults. I only want to see the female. So it allows a lot of selecting of observations I've been doing, and after this I will show why this is so important. So at this moment I have my deployment, my images are uploaded into a deployment, and I will go again to this deployment at deployment, because it's important over there that you have your list of sampling points. The list of sampling points can be uploaded in different ways. What we do most often is to upload a CSV, because you know the coordinates. There's an example CSV which shows you what it should look like. It opens. There you go. I will open it anyhow. So you get a whole list of possible locations at once, which allows you, if you have to add a deployment, to select out of the list of possible deployments or possible locations. This one is also an important one. So the time set, the offset compared to UTC, normally it's defined on the project level. So you create a project and you define the offset compared to UTC. However, it could be that in a certain deployment, for a certain reason, the camera was in a different offset, so you can correct it. Normally we don't touch it. Makes life a little bit easier. So this is the animals are annotated in the sequences, and I have a long list of observations of all the animals I've seen. In order to calculate for the observatory the random encounter model, the next step which we have to take is that we have to calibrate our images, and therefore I will use the old one because it didn't change that much. this we don't need anymore. So in order to be able to calibrate, I hope this is big enough. We go to the field and we say we'll do the deployment calibration. Into the field, which we explained in the first training, we go with these sticks. And on the stick, we have different heights, going from 20 centimeters up to 1 meter. And this allows us to stand in front of the camera and then walk around. And I guess Marcus will have a little bit more on this. We need at least 12, 15 of those sticks where we annotate two places, which is the top one. And you can order it over there and say, okay, this is the top of the stick, it's 1 meter. And I can click on the second place on the stick and say it's 0.6. And this way we go through the whole set of sticks in front of the camera. We agree with the team that we always put on our thumb to be sure, in order to avoid that people start to use sticks that were during the walk from left to right to annotate the images, or to calibrate a deployment, which of course cannot be the goal. That we are going to use this kind of calibration images which are not the correct ones. If I go back to Agouti, if I go back to Agouti and I go into the deployment, I will take this one. So in the new version of Agouti, it's this deployment calibration. Of course, there's no stick in this field, but you can see over there, you can now decide the top of the stick, the bottom of the stick, and go through the different images. And you will save it as a deployment calibration. The next step, if I have a deployment, and in the beginning of the deployment, I already made the calibration for several sticks. The next step I would like to do is I need to define the distances, and then the observation file becomes very interesting or very important. If I decide, looking to the observations, I will take away this. I'm going to look to a row there, and I would like to. So I already know, okay, there they are again, but it's a bad example, I'm afraid. Yeah, that's a bad example because it's running away from the camera. So I will take another one. Seven. Okay, let's see. I hope this one is a better one. It is a little bit a small one, but I will still use it. So I have a row there. It's an adult female, and now I would like to track the animal. So I simply start by the first image of my list, and I look, and I always take the place where the animal or the leg of the animal. No, go back. One back. Yeah, he's clicking there. So I'm tracing the animal through the different images of the sequence, and I save it again. The example over here is maybe better. So I go to the first. Important is that we click where the leg of the animal would hit the bottom of the forest. And if I don't see it, you don't have to guess. The most important is that we follow the animal through the whole sequence, and then you get this. So first observation, second observation, third observation, and we can track the animal. This information, these locations of the animal, together with the calibration of this deployment, allow us to define the location of the animal, and as we also know the time, we can define the speed of the animal through the sequence. Back to Agouti. The nice thing is that if we first annotated all the images, afterwards you can make a selection of which sequences we would like to score and to determine the distance on. Two questions which already came in the past, and will have a look. I will take away the female over here. They're all caprioles. No, dama. It's only one. Go to that one. Some stuff is a little bit difficult. One is if the animals run away from the camera, or they discover the camera and they run away. Don't use those images or don't use those sequences, because they're not the normal ones, or they're not the easy ones, or the reference ones to use. And the other thing is, which happens quite often, but I will take another project as an example. So here I have a actually show. I have a sequence of 430 images, which means that 43 times the camera has been triggered during this sequence. So there is a first shout if the animals are not clear, but there is a first fallow deer who comes into the image and then starts eating a little bit, then runs off. There is a second one. There is a third one coming into the image or to the sequence. Now the three of them. Now at the fully, still three of them. Let's see, jump a little bit. There is a fourth one. So I have a whole bunch of fallow deer which walk through this sequence, and for the defining the speed, we only have to select. It's quite often quite a hell to do it this way. So we simply select one animal, for example, the first one, which is quite often the easiest one, and track him from the first moment all through the. So that would be one of them, which you click and then you follow the animal and say again, save. Let's get back to the presentation. One of the things which which we had also in the deployments. Oh, now I'll go back to the project to play around. I will take that drawing hood project again. If I click too much, it will, in the observations of this kind of big projects, you see that we have observation times being species. And we have the different species I explained. And sometimes, most of the time, it's written over here who has been doing the annotation. But sometimes you see over there, Western Europe, so the artificial intelligence has been doing the annotation of the images. The modification quite often is when someone of us has been checking this, and you can do it also by going there and changing something if necessary to this observation. So the artificial intelligence has been going through, has been checked what's on, told me that 2 fallow deer of unknown, and the colleagues has been checking it. Why is it so important to check? One of the main reasons is that the species determination is quite okay using the artificial intelligence, but defining the number of animals is quite often very difficult still for the AI, because it's looking at image per image and it cannot see the total number of animals that are present in a sequence. Okay, so where are we at the moment? We uploaded the images, put it in a deployment. We went into the deployment. We looked at the sequences. We determined the species, if possible also the age and the sex, and the number of animals in each of the age and sex classes. Whenever in a sequence is more as one, or the 2 different sex age classes, they result in 2 observations, but those 2 observations will have the same sequence ID, which allows afterwards in the analysis to look at the number of sequences as a way to define the number of times, for example, Dama were observed. The observation list is finished, so we were also able to track animals through a sequence, and using the calibration images, the sticks in the field, we also could calibrate the deployment. Tracking animals is only useful within the deployments where the animals, where the deployment has been calibrated. Otherwise it's quite useless. One of the things we discussed in the past also was, if you have thousands of sequences, how will I do this? Or how can I select which observations I will track a certain species? Using the sorting of the observation IDs, given that these are pretty random codes given, we can use those to select a certain percentages. But once again, be sure that if you select a sequence to track an animal, they come from a deployment ID that has been calibrated. Otherwise, it's without use. So there we are. We have observations with species, with class and age, sex. We calibrated deployments, and we tracked the speed of the animals through the sequences. So we're almost there for the next step, being the analysis outside of Agouti. So we need to get our images out of the project. The easiest way to do this is to go to export data, and there we can, and I will create a new one, create export, and then you see this small wheel starting to turn. so now he starts to create an export for this project. It can take some time, so I will not wait for Agouti to do this. Let's simply show you what it looks like. So there is so what he downloads finally is a zip file. If I unpack the zip file, because there was some preparation for random encounter modeling, there is a position plots, otherwise I wouldn't see it. And then there are always three, there's the JSON, and there's always 3 CSV files. One is called observation.csv, it's the list of observation. The deployment CSV, it's the list of deployments. And the media CSV is the list of all the images belonging to a certain certain deployments and certain files. If I'll go back to here. So we annotated the images. We did it manually or we did it with AI. We calibrated the deployments. We tracked some animals. We created an export. We get the zip file. The important thing of the export is that it's a standardized export, which means that Agouti, Trapper, eMammal, Wildlife Insights, we're all going towards the same standardized export, which allows very easy to interchange files from different projects. It also allows very easy to interchange files between projects, which of course makes it a lot easier for the Earth Observatory, European Observatory, which you're working in right now, to put those files together and to check files, which makes life of Tancredi a little bit easier. That's the name of the standardized format, CamTrapDP. I will not go into it. But what it also is important is that in the meantime, there was another package created, which is called CamTraptor, which allows you to read very easy exactly this standardized export, and then starts based on this standardized export. You have a bunch of functions which allow you to read the data, to filter the data, but also to explore the data. This is not so important. To explore the data directly on a map, being relative abundance indexes, for example, or a lot of other questions which you can answer using this standardized format. And then I think we're at the end of what I wanted to explain, but as it was given on the flow in Agouti, I can imagine a bunch of questions, but given that I don't see you, I will first stop sharing. How can I stop sharing? Where are you? How do I stop sharing? Check.
Jim, at the bottom of your screen.
Yeah, found it.
Okay.
I was on the wrong screen. Okay, so normally I should have stopped sharing now. And I don't know if there are questions, if everything was clear, if it was too quick or too chaotic. Just shout and tell us. Okay, Mike has a question.
And I'll just start with my first one. That would be if there's any possibility to upload like pictures of several deployments at once, like of several locations, or do we have to do it like for every location separately?
For every location separately.
Okay.
And one thing which you should definitely not do is to add several screens of Agouti of the same project at the same time. In the beginning, we try to do it like opening 4 tabs of Agouti in the same project and then having uploading images, but it creates a tremendous mess. So
okay.
Yeah, the only thing, if it's really going slowly, the only advice I could give is take a good book or take some scientific papers and just start reading at the same time.
Yeah, okay, that makes sense. And my other question would be, since we are also uploading all of our projects on Trapper, if there's any possibility to just upload also the tags from Trapper to Agouti.
What do you mean with the text or the annotation of which animals?
Yeah, exactly, like the number of animals and the species.
I don't think so at the moment. Like I said, the standardized export allows you to combine information of the two systems, but not to import the export of one system into the other system. Now your mic is off.
Okay, because we still, of course, need to upload to Agouti for the tracking and the stuff that's not implemented in Trapper. So I guess, yeah, we would just need to do it twice then.
And you're still uploading them in Trapper to have the individual pictures, or why are you?
Yeah, and because we have all of our other projects on Trapper.
Okay, sorry.
Yeah, thanks anyway.
I don't know if there are more questions.
Yeah, there are a few questions in the comments in the chat. So the first one from Jorge says, so you don't need to track all the animals in the group?
No, it's enough to track one of the animals in the group. Otherwise with fallow deer and with wild boar, it becomes a mess. So no, it's not necessary.
Perhaps about this, I might have missed it, but we might give details about the minimum numbers. Like if you have, let's say 1,000 sequences, how many should be digitized as a minimum or an optimal number to have good estimates?
Yeah, I will pose that question to Marcus for the second part of the training.
Right.
Also because it's a problem, we never had. We have the problem that we have too many animals in the same sequence. So we solved this by tracking only one animal, but we never had the problem of having too many sequences. So I leave it to Marcus. The other question is, do we have to annotate only those sequences where the animal is walking normally? Or individual walking. I think you can annotate whatever you want. The way they walk is not important, but what is important is that you can see or estimate where the leg would hit the floor, which means that animals which are really too close to the camera, you cannot use them. And as I said before, and as Marcus also said yesterday or one of the days, animals that, of course, see the camera and then run off because they're scared. It's not the typical example of what you would like to start tracking. And so that's, I think, the answer to the zigzag. Are there any species that Agouti finds it more? So the AI is working better and better. What we still see, but it's based on our experience. We have an area with fallow deer and roe deer together. In the winter, it works pretty well. In the summer, small fallow deer are from time to time identified as roe deer. And what also still is a problem, and it's not a species problem, but it's an AI problem, is if the animals are really close to the camera and you see like just an ear or a nose or something like this, it becomes very difficult to find the right species. So what we did is that we always, if AI has been going through, we always check the images anyhow manually by going to the observation tab, selecting the species and checking if all the animals of a certain species definitely are that species. I don't know if the problem of different. Yeah, Camila, I don't know what's the reason. One of the points which you indicate definitely is true. if the model was never trained on recognizing bisons, he will try to make something out of it. We have the same in a project where we have grazing with cows, and of course the model was never trained to identify cows, so he tries to make something out of the cows. So I think it's the only solution for this kind of problems is that we start giving some enough images of this kind of species, which is really badly recorded or badly identified, and we provide those images to Yorick, or we ask Yorick to select those images so we can train the AI to better discover those species. But we're moving circles around the tree. If really two animals are moving in circles to Rhodia, I suppose it was in August, so it was during the rut, and I would not take them as a regular behavior. I mean, it's quite often it's a buck chasing a doe, so I wouldn't use it. But of course, it depends on the number of observations of Rhodia you have in order to be sure if you need it or you don't need it. But we sometimes throw away if they're too suspicious behavior or too low quality. I prefer to work with the good ones. But again, I think it's something which Marcus better can answer because it's how to deal with the data you collected rather than how to annotate or how to make the exports. I don't know if there are still other questions. I don't see anything in the chat, but I don't know.
Shall I go back to that question about sample size? Well, actually, before that, just to clarify my perspective on selecting or choosing or not to digitize particular sequences. The main decision point there is it natural behavior of some sort? So in that sense, that point about circular movement could be defined as natural behavior, so I wouldn't necessarily reject it myself. The key point at which you want to reject digitizing is if the animal is reacting to the camera. The reason is, you'll see when I talk about the density modeling, if the speed of the animal is affected by the camera, then the assumptions of the random encounter model no longer apply. So if you see an animal, the first thing you see is with the animal interacting with the camera, it's got its face in the camera, then clearly that's a reaction. So you shouldn't include that one. If the animal comes in initially showing no sign of having seen the camera, then it's okay to digitize that part of the sequence up to that point. But if it then stops and notices the camera and then either comes towards it to have a closer look or runs off, then you shouldn't digitize beyond the point at which the reaction becomes clear. That's the key thing to keep in mind there. On sample size, as a rule of thumb, if you can aim for 200 sequences digitized, or 200 individual animals rather digitized, around 200 digitized observations, that's a good sample to go for. It's not a disaster if you don't get that many. If you're only getting 10 or 20, then you're not going to have a very useful and precise estimate from that. But once you start getting to maybe 100, but certainly 200, you should be getting a good precise estimate after that. I hope that makes sense.
Mm-hmm.
So do you mean 200 per species and location?
Sorry, Mike.
Sorry, do you mean 200 tracked individuals per species and location, or?
No, per species, not per location.
Per species, okay.
Across all deployments.
Okay, great.
Yeah.
Thanks.
But just again, to reiterate the point about sampling, you should randomize the observations first so that you get a representative sample across observations. So Jorge just came back about if they're going in and out of range. Yeah, sure. No, don't. If you're getting animals leaving the camera but then coming back at some point, that's not a continuous sequence of behavior. So you should stop at the point they leave stop tracking at the point they leave the detection zone for sure.
More questions?
Any other question? So, because if
Yeah,
not,
I don't know if it was not too quick, or if everything was clear. I hope so.
yeah, if there's any doubt, this is the good moment to share.
Maybe one more thing regarding the calibration, because we also had a problem. It's important to click on the stick and then to define the altitude or the height, and then to click again on the stick and define the height again. We had a student who always made 2 clicks, bottom top, and then wrote bottom top at the sides, so filled in the heights, and it gave problems. So be sure to follow the logical sequence of this is the bottom 20 centimeters, this is the height I can see 80 centimeters, and not just start clicking and annotating all in one big mess, because that makes life very difficult apparently for the computer afterwards to know which height is for which marker. And another question which we had already is, it does not has to be the 20 centimeters. If you cannot see the 20 centimeters, but you can see the 40, then use the 40. It doesn't matter as long as we have 2, except if Marcus now contradicts this, but quite often the vegetation does not allow you to see the 20 centimeters mark. So
that's correct. Yeah, and just to emphasize again that do each point one at a time, so that the height you put in for the top definitely relates to the higher point on the image. It's something I would like to fix in Agouti so that it's not possible to get those mixed up. But at the moment, you can assign a lower point to a lower height value to the point that's higher on the pole, and that, yeah, as Jim said, that confuses the machine. So.
One thing I've been asked a few times is about the uploading of large sample sizes. So when you split in more than one deployment, and how does that work with the calibration sequences, and whether the calibration sequences do apply to the other deployment of the same location, and that sort of information.
So as far as I get it, the calibration is linked to the specific deployment, so not to the location. So if you there was already some questions if we could not like transfer the deployment calibration to a second deployment on the same location, but until now we did not. One of the reasons for us is that quite often the camera has been moved a little bit, like by deer or by wild boar bumping into the camera. So it's depending on the deployment, specific deployment. If you have a deployment with plenty of images on its own, it's not a problem, because you can upload like 10,000 images into one deployment. Agouti will not complain. Maybe he will complain by the uploading, so you better upload them like 3,000 at a time, and then a second time 3,000, and a third time 3,000 until everything is there. But if they belong to one deployment, just keep them in one deployment. Otherwise, you will get problems. And I see there still is a question.
Hey, hi everybody. Just a question. For example, you made the first calibration, you installed the camera, and then the animal moves the camera, and you will have a second calibration. How to deal with this kind of information when the camera is moved and you have two calibrations and two sets of pictures with different distances?
Subdivide them in two deployments. I think that will be the only solution.
Okay. Thank you.
More questions?
So if no other question is to be asked, we are quite far ahead on the schedule. We could have the 15 minutes break now, and then if in these 15 minutes any other question arises, we can then address it as we come back. And if not, then we can start with the second part of the training.
Okay.
Okay, so I'll see you in 15 minutes at 20 past 10. Still about the loading of deployments and that kind of topics. Jim, you think you can take on from about those questions?
I'm having a look at them.
Right, thanks.
So regarding the first, taking away blanks, yes, it's possible. We always argue against, for the simple reason that other scientific questions could maybe not be answered then with this kind of uploaded sequences. Imagine we would like to know how often they create blanks compared to animals or this kind of stuff. It will never be documented that the blanks were manually excluded. But yes, I mean, many people do it to avoid too many images. So yes, you can do it before uploading to Agouti, except the first and the last ones, or at least some of the first and the last ones, because Agouti is using those photos or those sequences to determine the start and the end of the deployment. Of course, what we also sometimes have is that we have like a 300, 400, 500 images of the people being pickup setup, and we just reduce it to 20. I mean, it doesn't matter if it's 10:30 or 10:35 when system starts. So that's question number one. After photos for deployment. Okay, the second question isn't clear to me, so that one should be explained maybe a little bit more. Not today, but it's such a sclerosis. And the last question. Okay, those are the Brownings. I don't work with the Brownings, so someone else should answer that one. The time lapses are normally not presented to calibrate because they don't make sequences. I don't exactly see how it comes that the calibration sequences are recorded as time lapses. Because normally they should all be motion pictures and the time lapses are only at a certain hour of the day to check if the camera is still working. So maybe the two people asking the second and the third question should maybe explain a little bit better or a little bit more the exact problem. Diego?
Diego, can you give a bit more details about? I'm not sure if you have the possibility to switch the mic on, Diego. Anyway, yeah, I mean, I would say that you can set the camera only on trail mode. The time lapse is a plus. I would say that makes sure that the camera has been working constantly throughout all the period of activity. So it is, if you can use it, then it's better. But if it's somehow messing up the camera trap activity, then it would be better not to use it. Okay.
Shall I see if I can say something about Sandeep's question? I'm also not entirely sure. Get clarification, but I think the issue is that you're collecting more calibration images.
Do you hear me?
Hello, yeah.
Yeah, so about this time lapse, the problem is that sometimes the time lapse in Browning, I don't know why, it just record our movements while we are calibrating. Especially if we are doing it in the morning, it's like the time lapse in this this special file that Browning has for it, and we cannot use calibration in that case. It's very, very weird, but so this is true.
I don't know if it was just me. I couldn't hear you properly. I can't hear you, Diego.
Yeah, your microphone is not working well somehow, Diego, I'm afraid.
Sorry, wait. Okay, do you hear me now?
Better.
Okay, so the problem with Browning is that I don't know why, but it takes like a sequence, make a time lapse with actually people or animals moving in front of the camera, sometimes, not always. So we found that a whole sequence of calibration is in that kind of file of Browning for time lapse, which is totally unusable because you just can reproduce these files in a video player. So I don't know why it happens, but I was wondering if somebody working with Browning had the same problem and knows how to calibrate properly, how to configure properly the time lapse, or is it better just to don't use time lapse at all with Browning to avoid this problem?
I've never used time lapse with Browning, I'm afraid, so I don't understand the issue quite.
Yeah.
I've not encountered it.
It's crucial to use the time lapse, or we can just avoid it and work in trial mode. That's all.
I think so.
Yes, as Camila is writing about this topic, saying that they also had issues and couldn't actually use the time-lapse mode. And so, yeah, it is. We also had some issues about that. So, yes, if you're facing these kind of issues, the best solution at the moment is certainly not to use the time lapse. Still, yes, as Camila suggests, you can try and get in touch with Browning support and ask more about that. But for the moment, if you're having these issues, just use the normal trail mode and go ahead with that.
Okay, thank you very much.
You're welcome. So Marcus, you try and answer.
So I think Sandeep was asking if you have you want to apply calibration images to multiple deployments, perhaps if the camera is in the same place. I think so. You have just one set of calibration images that might apply to multiple deployments. That's possible in principle. So and you can deal with that by just adding the same set of images to each deployment for which it applies. So when you upload the images, you add that set of calibration images. You might need to do some renaming so you don't have name clashes. But you need to be very aware that that will only work if the camera is in precisely the same position. If the camera has been taken down and put back up again, it will definitely have a slightly different point of view, which requires a new set of calibration images. So you should only do that using the same calibration images if the camera really has not moved at all.
Perfect, thanks. Okay, and she also confirms that that you answered the question.
Okay, so I want to start with a quick reminder of how the random encounter model works. We'll be talking about fitting several different types of model. So I want to just refresh on why we're doing all these different models and how they fit into the overall density estimation. So let me start with a little animation. So go here. Can you right, so just to check, I hope you can see my screen changing. Can you see a bunch of green circles with a dot moving around? Okay,
yes.
Great. So this is a little simulation. You can think of the black dot running around as an animal moving across the landscape, and the green circles as the detection zones of cameras. Every time an animal passes through the detection zone, we count it. Doesn't matter that it's the same individual. We don't need to keep track of which individual between encounters, but each encounter here becomes an observation that we count up, and you can see that counter in the top right going up. In this case, we've only got one animal. If we were to put 10 animals in, the we'd get more encounters, you can imagine. So the trap rate is related to the density of the animals. That's not the only thing that affects it, though. It's also affected by speed. If I were to speed up how quickly all the animals were going, that would also increase the number of encounters that we observed. Also, if I were to make the camera detection zones bigger, we would get more encounters. So the principle is that if we know the trap rate and we can control for speed and detection zone size, we can extract a density signal from that. This is a slightly different simulation where still one animal and the detection zone is the same size, but the animal is moving in a more tortuous way. It's turning much more often. And that indicates that the trap rate is unaffected. So the fact that animals don't move in nice, perfect straight lines is fine. But you just get more concentration of records at particular camera trap locations. So we can understand how the process works a bit better from this. The key thing, again, is we know that animals don't move perfectly randomly, but the key thing is that cameras are placed randomly with respect to animals. So that's a crucial design assumption. So we need to try and make sure that we're not targeting good places for animals, or indeed not missing them. If they occur in the environment and our design happens to put the camera there, that's fine. But we shouldn't be thinking about that when we put the camera up, just placing them in the place, the randomized or the systematic grid position that we predetermined. Okay, so I can get rid of that. So just to put that in textual terms, animal density is a function of the trap rate. It's a function of animal speed. It's a function of activity level. So we break down the overall distance traveled by animals into the speed whilst we observe them, which is whilst they're active, and the proportion of time spent active. And we characterize the detection zone not as a circle, but in actual fact as a sector, part of a circle. So you imagine the camera at the point of the sector here, and the size of that sector is characterized by its radius and its angle, so how wide the field of view is. And we can estimate all of these parameters to control from the speed, activity level, and detection zone dimensions from the data. And that's why we're doing the calibration, is because it gives us information on how far the animal is from the camera. Once we have those animal positions for sequences of movement and where they are when they first arrive, we get information that we can use to fit models to estimate these parameters: speed, activity level, and detection zone dimensions. So we'll see how that works in practice in a minute. So just to practicalities then, how do you get started? I'm sure a lot of this will be just refreshing memories. You've all been through, I think, well, at least the majority of you have been through rounds of doing analyses, but I'll start from the beginning just to make sure that everything is clear. So the first thing is that you have exported your, this is where Jim left off, you've exported your zip file data package from Agouti. So I've got one here called the REM test. I've put it in a meaningful folder. So I've got my Enetwild folder, my analyses, I've got my REM test. This is the specific analysis that I want to do. And the first thing to do is to unzip this folder, or this zip here. So now I have my unzipped folder of data. I look inside it, see that I've got a bunch of things. I think Jim touched on this. We've got the CSV files, so simple data files that contain all the information we need, and a JSON, which is all the project metadata, which we also need. So we don't actually need to worry about this, but if you're interested, you can dig around in these files just so you can understand a bit more about what's in them. In practice, we're going to access all of this through the R interface. And we're going to be using particularly the package Camtrack Density. So the key place to get this and to understand how it works is here. So if you go to this website, github.com, Marcus Rowcliffe /Camtrack Density, you'll have a pretty uninformative page at the top, but on this homepage for the package, if you just scroll down a bit, you'll find the README section, which is where we get some more human information about the package and how it works. And in fact, there's a step-by-step tutorial. So what I want to do is just step you through this tutorial so that we can see what the options are, how it works in practice, what the workflow should look like. So the first thing is, if you don't already have them, obviously you need to install both R, which is the underlying analytical engine, and RStudio, which is a user interface for R. So once you have both of those downloaded, we can get going. So the first thing I want to do is, once I've done that, once I've installed R and RStudio, I want to fire up RStudio. You don't need to access R directly anymore, so RStudio runs R in the background once you've started Studio. So once you open RStudio, you'll see this. This is a clean session. If you open it for the first time, you'll see this. Got your blinking cursor. This is in the console. So this is what you call a command line program. So it does require you to run bits of code, which is I know a bit intimidating if you're not used to that, but what I've tried to do with Camtrack Density is to make the functions as easy and legible as possible, so that we can it's as accessible as widely as possible at this point. So with the console, you can do simple calculations. You can start to run code. You can use functions. So, but in general, when you're doing an analysis, you don't want to run your code from the console. You want to keep a record of it so that you can reuse it. You can edit it. It's not efficient to run it in the console. So the first thing you want to do when you fire up is to open a new project, in fact. So we're going to run all of this within a project. The benefit of projects is that you can save your code, you can save your progress, you can save the data objects that you create within the analysis. So the first thing is to create a new project, so file, new project. Just a moment. So there's various ways you can do this, but I would suggest creating your project within the same directory that you put the data export from Agouti. So I'm going to say existing directory and then browse to the place that I put it, Enetwild, Analyses, REM test. So I'm going to say that's the directory that I want to create the project in, create project. Okay. So now we have an extra pane down here. You can see my environment is empty. I haven't created any R objects yet, so I haven't started. But I can see a new tab down here called Files. And we can see this is exactly what I looked at in File Explorer. We've got the data folder, the original zip folder, and now we also have a file with the extension rproj. It's an rproject file. And it took the name of the project from the folder in which I put it, which is great. That's fine. That should be meaningful and be easy to keep track of later. So you can, if you need to get back to that, you can do that. Next time you want to, if you've finished doing some analysis, but you want to come back to it later and you want to restart RStudio, you can do that in the same way that I did, just choosing from your application chooser, or you can just double click on this rproject file and it will start up within that project at the point where you left off. Perhaps if you've saved your progress. So that's a convenient feature of using projects. So the first thing once you've got your new project is to start a new code file. So you want to start a new file, a new R script. So now this creates another new pane. Now you've got your fourth pane. That's all you're going to be working with. You can see that it's just an empty text file, essentially waiting for some code. Just going to move this over here. So what to do first? So the first thing to do is to make sure that you have the necessary functions. We're going to be using a range of different functions from Camtraptor, Camtrap2R, you prefer, and especially Camtrap density. So we need to make sure those are installed, plus some other packages that support those two primary packages. So the first thing to do is to make sure that you have necessary packages installed. So the first thing I would do is use this base R function, install packages, to install something called dev tools, development tools. And I want to install something called tidyverse, which is it's a package of packages, in fact, that make life easier in a range of ways for manipulating data. I'm not going to run this myself because I already have them installed. Once you have that, you can install the key camera trapping packages we need for this analysis. So I'm going to do this makes clear that I want to use a function from the DevTools package. So that is install So at this point, I'm using a different way of installing these packages because they're not yet fully released. They're still developing quite rapidly. So we don't yet have stable releases that are on the normal package repository. So this first one here, these are stable packages that have been out for some time. You just, this default use knows where to look of install packages. We're using a more specialist, two ELs there, a more specialist install from GitHub, which is a program development environment. So to install Camtrap 4. So I would run this, just copy and paste that and replace that with Camtrap density. So if I run those 3 lines, As I say, I'm not going to do that myself because I already have these installed. That should make those packages available. So this I need to do only once. It should be, or maybe from time to time, if there are updates, you may need to rerun these to install the latest version. But certainly not every time you run a new session. So I'm going to draw a line under those. That's not something I have to do every time. What you do have to do every time you start a new session is to load those functions using those packages using the function library. So to load camtrap to R, to run that, and similarly to run camtrap density. So those functions should now be available. Do it in a more point and click way. If you look here, you can see that those two packages on this tab here, you've got a list of all my install packages. Most of these have not been loaded for use in this session, but camtrap density and camtraptor have been now. So now we can start doing some analyses. We can load data first and foremost. So what I'm going to do is to create an object called package. You can call it what you like. I find this is a useful short form. The key thing with choosing the names of objects in R is to use something that is as short as possible. So you have to do minimal keystrokes, but as long as necessary to make it clear when you come back to it, not having looked at it for a few weeks or months, what that object means. So arguably, this short name package is not the most meaningful, but I think in general, it's because it's a really fundamental way in which the data are organized. It'll do for now in this case. So the function I'm going to use, oh well, first notice I've got this arrow, which is the less than sign and the dash. You can do that in one go in Windows at least with a shortcut Alt dash, so slightly fewer keystrokes. And the function is read underscore. So we've got a choice of those. You'll see that I have a list of the possible options that match that. It's quite a nice feature. So we've got the camtraptor function, read camtrap underscore DP, or we've got the camtrap density version. The camtraptor is going to be upgraded very soon and has a few features which are not quite optimal for the density analysis. So for the time being, I recommend that you use the camtrap DP, read underscore camtrap capital DP from the camtrap density package to read the data. So because my project is in the same directory as the data folder, and that is the working directory, I don't have to type the full path at this point. I can just start from where I am in the working directory as implicitly understood. So remember the data. We go back to files. The data were in this folder here. So just need to complete that. 2024, 305. 145652, 145652. And then within that, I want to point to the JSON file. Go back here, data package, .json. Just check that that all looks right. That ran without problems, which is great. And you may notice that now this environment that was empty has this object that I created called pkg package. And that contains all the data that we need in a nice structured way, so that the functions that we're going to use know where to look for the information that they need. So that's great. We don't want to dive straight in and run the density analysis. We need to do a bit of data checking. We need to make sure that everything is structured right. I think as many of you have found, there are various problems that can crop up. So we need to make sure that everything is structured okay first. So the first thing that I would do is to just visualize the deployment schedule. So do all of the dates of deployment look right? So did they occur when you expected them to occur? Sometimes the cameras can reset the date, or the user can set the wrong date. Visualizing can help to throw up those kind of issues. Sometimes you can see observations have been tagged at dates that don't fall within when the deployment was supposed to happen. Visualizing again can help to show that. So what we can do is use this function here, deployment schedule. And all we need to do, pass into that function, is the data that we want to plot for the project. So I'm just going to tell it that I want to plot the deployment schedule for this data package. And then I can run that. I should have said this is, again, basic R, which I'm sure most of you are totally familiar with, but you can use the run button here with the cursor on the line or the group of lines. If you want to run all of that code, you could run that. If you just want to run one line, you can just have the cursor on that line and run. Or I usually use a keyboard shortcut, which is in Windows at least Control and Return. So we get a plot like this. So it might be nice to use the zoom function to make that a bit bigger. So then you can get a full screen view of that. So we've got 4 different locations, or 4 different deployments, I should say. One of those, actually, this doesn't make a lot of sense. I've got 2 deployments at the same time at the same location. This was just for illustration. I created a notional extra deployment, but actually that doesn't make sense. You wouldn't see this normally, but it's possible. You can see that it's possible to have multiple deployments at the same location anyway. Usually they would be separated in time, of course. So the black line obviously indicates the beginning and end of the deployment, and the orange ticks, the lines on those, indicate when observations happened. So there's no immediate issues that I can see here. They all occur in roughly the same time. Sometimes if you have, automatic camera resets, you might see one or a few deployments that happen in a completely different year, for example. But you can check the actual dates and times of these by hovering over the observations. You can see the deployment ID, which is a complicated long string of random characters. But if you need to trace that back to use that in order for correcting things later, you can get the deployment ID from that. You can also zoom in or out if, this is a fairly easy to read plot, because there's only a few locations and not many observations. It's a small set of test data, but you can use the drag function to zoom in like that. Can go back to full screen there. You can zoom in like this. You can pan around. Yeah, so it's quite a nice, easy way to explore the data. So that can help you to just check that everything lines up and makes sense. So I can shut down that Zoom screen now, go back to my R Studio interface. Assuming that we did find some problems, we might want to try and correct those. Might mean going back to Agouti and redefining the start and stop times of the deployment. But if everything is shifted, so the observation dates and times are also wrong, then that's not going to be possible. So in Agouti, so you might need to do some correction of the data within the R environment first. Oh, sorry, just to say before I go on to that, there's a couple of other little explorations you can do. Camtrap2R also has some of these visualizations. At the moment, I'm more familiar with the functions that I have within this package, so I'm going to show you these, but explore the other options as well. Ultimately, you know, this is developing alongside Camtrap2R, but the idea is ultimately that these will converge. So they should be developing very similar thinking on how we do these things. So there's a couple of things that you can do to map things. So you can, again, just pass that package into a function called map deployments. That gives you an interactive map that just shows you where the deployments are. So these were around my office in London. You can map the trap rates or relative abundance index. So there's another option there. So at this point, doesn't immediately know what to do because there's multiple species and it wants to do it by species. It's not going to, at the moment, there isn't a function just to map overall trap rate, although that might be something nice to add, but at the moment it assumes you want just a single species, but it needs to know which one. So it asks you down here in the console, which species do you want? So if I want to plot, say, fox, and it gives you a little summary of the data that you might be interested in for REM analysis. I'll come back to that. But at the moment, I just want to think about which species. So I want to look at the trap rates for fox. That's the second species, number 2 in that table. So I type a 2 and I press enter. It says Zolpes, fox selected. Again, I get that same map, interactive map, but now with the points scaled to the trap rate, so records per 100 days. So we've got probably between 30 and 50 records per day. A lot of foxes in Regent's Park. Per 100 days, I should say. So one every other day or so. So that could be quite interesting, looking at the distribution and the overall rates of observations that we're getting. So going back to what to do if there are issues with some of the dates and times in your data. So imagine that you look at a deployment in the deployment schedule. So if I go back to this, so I looked at this deployment here, and it says it started at 6:06 in the evening on the 2nd of October. And I know that that was wrong. Somebody set the date wrong. It should have been 12:30 on the 9th of October. So how could we correct that? So we can use a function called correct time. And we are going to create a new package now. So we need to make a new data object that is the altered data. So the fundamental information within the data package is going to be changed. So we don't want to create an object with the same name. Best to keep that unchanged and create a new data object that holds the corrected time information. So again, we're going to use this assignment. We're going to use the function called correct time. And we're going to first and foremost pass the package into this. Now we need to give it a bit more information though. So this is what we call the first argument. We're going to need a few more arguments. So you could type these arguments in here on the same line, but just to make it a bit more legible, I'm going to put them on different lines. So first thing we need to do is give an indication of which deployment we want to change. So we're not going to change every deployment using this. We just need to correct the date and time for one particular deployment. So which is that? So the argument name for this is D. So I'm going to hover that there so I can see the deployment name. It's going to be D2, F2, E1F. This is a bit of a pain. I'm thinking about ways to try and make this easier ultimately, but now this is what needs to be done. Oh no. Okay. This all needs to be, I forgot, this all needs to be in quotation marks. It's called a string text, so a text string rather. So I'm just going to double check that all looks right. Yeah, right. I think that all looks good. So we're not done yet. We need a couple more arguments in here. We need to give it some reference times in order to say how to change them. So again, looking at the deployment plot, I can see that the time at which the machine thinks the deployment started was the argument is called wrong time, and that time was 2017. to 18:06:43. And I think I said that we know that the right time, the time we want to reset that to, was same year, same month, but let's say on the 9th of October, and it was at 12:30 on that day. So something went wrong when setting the camera. Just need to reset, get everything on the right time. So if we run that, so that all seems to run fine. Let's check that again. Check the new package that we've just created. Which 2? Okay, and you can see that it's changed. So this deployment here, everything is the same in terms of where the observations were relative to one another, but we now have the new deployment timestamp at the start. So that's a way of shifting for a given deployment all the times up and down. I know there are potential cases where it's a bit more complicated than that, in which case we don't have an easy function for that yet, but we need to do a bit more in-depth programming, but I won't go into that here. It's hopefully a minority problem, but just be aware that it is possible to deal with more complex correction cases if really necessary. We may also want to take a subset of the data, so slice it up in different ways. We may want to use only a subset of deployments. So for example, if several seasons have all gone into the same project, I think in general, it's probably better to create different projects for different seasons for the purposes of analysis, at least. But I know sometimes multiple seasons have gone into the same project. So if you want then to get the analysis for a single season or a data package, just for that season, you can create a new data package here, which is using a subset of deployments that maybe are just for one season. So subset deployments. So again, we just pass in the original package. Or let's say we're working down the package versions here. So we've corrected the wrong times for that first location. Now we need an argument that gives some information about how we want to select the how we want to select the deployments that we want to discard or keep. So the argument for this it's just the second argument. It does have an argument name. If you want to remind yourself what the arguments for a given function are, you can run this. So set deployments. So if you run that, you can see that there are just 2 arguments. First is called package, the second is called choice. If you can name that, I could do choice equals and then write something, or I could just start writing something here. Because it's the second argument, it automatically matches that to the choice input. So I look at this again. Maybe I want to discard this deployment here, which is the only deployment at location 2. So I can use location name is equal to, so it's a double equals. I should say, sorry, not equal to. So this will say return all of the locations except any that are equal to this O2. Okay. So if I do plot this new package now, should see that the location SO2 has vanished. It's no longer in the data set. It's just the remaining locations that we can analyze. Various other ways that you can do this. I could have said, for example, start. So this is the internal data column that defines when the deployment starts. So I could say start is, let's say, before the so the 22nd of October, just to pick a date. So that would be another way to have excluded that location. Slightly different way in which I've given it a date time here. So this is a function, it's actually from the LubriDate package. So you can either run it that way or you can load the LubriDate library first. So this is one of the sub packages of tidyverse. So that means that this text string then is interpreted as a numeric date, effectively. So you can run things like that. There's more examples on the GitHub README tutorial, so go and play with those and see what works. You can use that to quite fairly flexibly select different deployments. The other thing is that you might want to slice up the interval that you want for these. So you can just another example of the way you might want to slice things up. So we can use a function called slice. Scantrap DP. Again, we just pass in the package that we want to run this on. So in this case, let's say we want to only analyze between a starting point of, and we don't need the LubriDate. I'm going to harmonize this when I get a chance, but we don't need to use the give date input. We can just give the string and it gets converted internally. So let's say we want to select only deployments that were between started between the 9th midday and finished before, basically the information that occurred between, let's say, the 9th and the 26th. So again at midday. So if we run that, so that just slices things up. It didn't affect any of these deployments at locations 1 and 3, but location 2 just got sliced at the 26th of October. So that can be helpful. Again, that's maybe not all of the functionality we want yet, but these there are similar functions going to emerge in the next version of CamTrapTel, so things should get easier in time, and that we'll get more tools available for this sort of data manipulation. So we're still just in the data correction phase, but I think the next step we can probably, once we're happy with the data we want to analyze, we can move on to density estimation. But I'll just take a quick pause there and ask if there are any questions at this stage. No, everybody happy? Is everybody there?
Yes, yes, it seems like you've been very clear.
Good, good, excellent. Okay, so it can be really quite simple from this point. If everything is nicely organized, we have the useful data, we can get running. Oh, there's one actually crucial thing we need to do in terms of checking first, which is checking our deployment models. So I'm going to take a bit of time to explain how to do that, because this is a very important aspect of making sure that we have robust density estimates. So the function that we want to run here is called check deployment models. And again, it's just a simple case of running a package through. So I'm going to use my original raw data package for this. This outputs a new data package, which flags each deployment as to whether it has a good calibration model or not. So call this package 2. So again, I'm assigning the output of this. It also has the effect of giving us some plots by which we can make a decision. So we, the user, have to make a judgment for each deployment model as to whether it's usable or not. There are no calibration poles. That gets flagged as there. Well, it's impossible for it to create any distance information anyway, so they won't even try. But sometimes we can have maybe a poor calibration model that's likely to give us bad distance information. We want to make sure that that isn't included. So we have to do that by making a user, as a user, make a judgment call for each deployment. So if I run this, check deployment models, I get a new window here. So what on earth does that all mean? So I'm just going to leave R for a moment, go back to PowerPoint, and talk a little bit about interpreting deployment calibration plots. So there is a document that is available on the GitHub site. It's if you follow the README, the section that talks about assessing calibration deployment plots has a link to that document, so you can get some more information there, but I'll just talk you through the key points of it here. So first off, how do we interpret this plot? So what the calibration model is doing is enabling us to take the animal digitizations, so we know where in the image each animal is. So each point on the ground under the animal that represents its position in that image. We want to be able to predict from that how far it was from the camera. And that then enables us to build our parameter models that go into the density estimation that I'll talk about in a minute. What this is showing is it's a plot of true distance from camera as a function of relative Y pixel position. So in this plot, each of these points that you can see, there's a point here, some points up here, is one of the poles that was digitized in Agouti. And the lines here, it looks like a single line almost, but actually there are 3 different lines that are plotted on top of each other. This curving line running through the points is the lines of model fit. So how does that relate to what was going on in the image? Here's one of my calibration poles. The relative Y pixel position runs from 0 at the top of the image down to 1. And then potentially if the base of the pole was below the bottom of the image, you can have values greater than 1. So this is a pole that was very close to the image, less than a meter. So we can still draw some inference there. Actually, it's worth saying that if you're digitizing animals, it is still possible to make a judgment call. If the animal's head was here, but the foot was maybe down here, it's still potentially worth digitizing that. We want those very close distances. We'll get reasonable estimates that that was definitely a very close animal. So it's still worth having those points digitized, at least for the first when the animal first appears. We can use that for the detection zone estimation. It's not so good for tracking movement, obviously. So maybe there's no need to track beyond that the image where it first appears if it's that close, but it's still worth having for that point. But anyway, back to interpreting the calibrations. We know that this pole is a certain distance away because we use a simple computer vision model. We know that these points on the pole are a certain distance apart. We have the camera calibration, which tells us the lens and focal length properties that enable us to then say with a good degree of certainty how far away that pole was. And we know the ground position, so that gives us the Y pixel value for that distance. So that's how we end up with these points that tell us where in this space on the graph that pole fitted. The lines then are a statistical model fitted to those data. How would we interpret this particular model fit? Well, we can see that there's a reasonable number of points. There's about 10 points here. That should be enough. I think we recommend that you get 12 to 20 points. When you're in the field and you think you've taken a pole position, you can't always guarantee that the camera has captured it. So we recommend doing more than that to enable that you have a good spread, and you get enough of them. But yeah, if you end up with around 10, that's usually enough. And the points are on the lines pretty much. So the model curve runs through the points in that space very nicely. So that looks like a really good fit. Also to note that the lines are very, as I mentioned, there are in fact 3 lines here. It's hard to see them because they're so well aligned. That is what you expect to see if you have very nice flat ground. The horizon is level. Also worth noting actually that the horizon here is a little, not quite halfway down the image. So you can see that around 0.5 here, you get the vanishing point of this curve. So that's where the horizon is, roughly just where that curve goes to infinity. So you can interpret it that way. So that's a very nice calibration. It's easy to get good calibration curves on that sort of ground. Of course, our models don't always look like that. Oh, just, yeah, I'll give that a big tick. That's a good calibration, so we want to accept that. Here's another example. So again, we've got sufficient points. There's a dozen or more there, 12 or more probably, I count them. The lines are not all on top of each other this time, and we see more separation in the points by color. So what's going on there? You can see the shading, it says here, is represents the lateral position. So if I just go back here, the darker points the poles would have been on the left-hand side of the image. The paler shading of those points, it would have been on the right. So, and we can see that the regression of distance in this one with the regression of distance with pixel position varies across the image. So that would indicate that the horizon is not level, it's kind of running across the image. So this was probably set on a slope. And the change in distance with pixel position depends on where you are laterally in the image. And you can see that the lines still fit quite well to the points of the relevant color. So the darker line here runs through this darker point. As you go across, you've got the paler points getting closer to the lines of which are paler, so on the right-hand side of the image. And the points are all roughly on or within the spread of those lines. So that, again, is a good calibration image. The ground doesn't have to be, you don't have to have the camera perfectly aligned with any slope, and the horizon doesn't have to be perfectly level. It's better if you can get it that way to some degree. If there's a very heavy slope running through the camera like that, you're probably not getting the best view, but we can still work with it. Doesn't invalidate the calibration. It still works. So that's good. We can use it. What about bad calibrations? So that's a horrible calibration, really nasty. So we got insufficient points for a start, only 3. The points really don't match the lines, so they're not on or within. They are within those lines, so that's something. But something has clearly gone very wrong with the fitting. So that suggests that basically there's no regression of distance with pixel on pixel position on the right hand side, but the horizon is pretty much, well, yeah, the horizon is off the bottom of the image on the left hand side. So in theory, that's kind of possible, but it would be a really, really bad placement if that were the case. And this is probably almost certainly a function of the machine trying to fit a model where it just has not enough data to make a sensible fit. So this is really not a usable calibration deployment. It'll give you some really crazy distance predictions. So we would definitely want to reject that one. Here's an example of some lines that look a bit more credible. Usually you would expect to see a sharper, a more rapid upswing in the curves, so that might be a bit of an alarm bell. But simply the fact that we've only got 3 points again suggests that that's not a good, not likely to be a reliable model. There's not enough information there really to estimate the rate at which the curve goes up as you move up the image. So we would also want to reject that one. Then you get sort of models which look like they might be kind of okay, but there are one or a few points which look to be outliers. So there's sufficient points here in principle, and some of them look to be kind of describing a sensible sort of regression of distance with pixel position, but those two here just look wrong. There's something going awry there, probably. So this one, we wouldn't want to use it as it is. There's something that we might want to try and fix. In fact, we might be able to salvage a usable calibration model in this case. The reason that it arises, there's two reasons, likely reasons. One is that the ground is very rough. So if it's you're working on boulders, or there are big cracks in the ground, and maybe one of the poles, maybe this pole here was stood on top of it was down a hole in the ground, for example. So it should have been across here, about halfway up the image, but because it was down a deep trench running across the ground surface, it got shifted all the way over here, something like that. So there's not a great deal you can do about that in terms of the ground surface, but if the ground is not too rough, there just happened to be one small trench, it would be reasonable, and the animals that you're tracking are mostly just going across a reasonably smooth surface. Otherwise, then you could simply go back to Agouti and delete that point, that pole, delete those pole digitizations from your calibration, re-export, and you'll then have a better chance of having a good model here. So the other reason is that just bad digitization, that you got gave it incorrect height information, is a common thing that's easy to do. You need to try and make sure that you double check those, get those right. But again, if you go back and check those calibrations that have this sort of pattern, you might find that some of the distances are wrong, and you could correct those and everything will be fine. So I've given that across. You want to reject it in the first instance, but as I've explained, there are a couple of ways in which you might be able to salvage that calibration and use it ultimately, which will be a good thing if you can. Yeah, there we go. So I think that's everything. It might be worth just pausing there again in case anyone has any doubts or questions about that calibration checking process.
Yeah, I just would like to say that all the understanding of these steps is fundamental for a good outcome of the analysis process. So if you have any doubt, ask them now. I mean, there's still gonna be time then to watch again the recordings, but yeah, if you have any doubt, please just go on with the questions.
Okay. That's okay for now. Yaz Tancredi says no problem to store up questions for later, but for now I'll press on if everyone's happy. So just to show how that looks in practice in running these checks in R, I've run this check deployment models on my data package. I'm in an interactive mode now, so I want to put my cursor in the console next to where this question is asked. So it's asking, is this a good deployment? Do I want to use this deployment for generating distance data and analyzing density? Worth saying that if I say no, it's not going to completely throw away that deployment. It will still use the information to calculate trap rates. Okay, so animals that appear in that deployment will be counted purposes of track rate. I just won't be using any of the distance information for calculating any of the other parameters, which is fine, just to be clear about what that's asking. So I just want to either input a Y or an N for yes or no. So that's a good deployment. I like it. I'm very happy with it. It has all the good characteristics which I just described. So I'm going to say yes. Hit return. And then the next one comes up. So the last one was one of the SO3 locations. This is SO2. Again, this is actually the example of a good calibration that I started with. So I definitely want that one. Next one comes up, SO1. Yeah, and this is possibly a bit more sketchy, not getting to be rather few points, but actually I don't mind it. I think this is still probably a usable. We can see that regression across the image. It's probably just about sufficient. So that's a case in point of a judgment call, which might be slightly marginal, but I'm going to go for a yes on that. Some of those, I think, not to agonize over it too much. If it's really borderline, including it or not probably won't make much difference, almost certainly. So just make a judgment call and see where you get to. So this one looks great. Really, there was the horizon was a little bit slanted on this one, but that's fine, not a problem. The way that the shading of points matches the lines is good. So again, it's my fourth one, and we end up with the cursor flashing against the arrow sign. So that shows that we've finished. We've checked all of the deployments, and we've indicated whether or not we want to use them for distance purposes. So now we have this object here, package 2, which is what we want to take forward for analysis. I might have flagged some of these as no, I don't want to use them for distance, in which case the data would record that response and act accordingly by excluding the distances from those calibrations, from those deployments. So I'm ready to do a density estimate.
Sorry, Marcus.
Yeah.
Perhaps there's a question in the chat about the calibration. So maybe it's worth answering it now.
Sure. Let me see. I can't. I'm not sure I can see the chat without.
Yeah, I can read it for you. It's not a problem.
Read it, yeah.
Sandeep is asking, are these calibration affected in any way if the cameras are placed on slopes, but parallel to slope and across the slope?
As I said, in principle, putting it on a slope is not a problem. They can deal with, if your slope is like that and your camera is facing across, the horizon is going to slant down through the image. That's fine. It's a bit inefficient because you're missing lots of ground that you could see towards one side of the image where the slope drops away. So if you can, it's good to place the camera slightly angled so that the image then has the slope more level across it. So the camera itself doesn't have to be upright. It's better to place it so that it kind of matches the slope to make the ground appear a bit more level. It's a bit counterintuitive, but it's not a problem if you end up visibly seeing the slope in the image. The calibration should be able to cope with that. The key thing is that you have sufficient calibration pole images digitized right across the image, both side to side and back to front as you move away. Does that make sense?
Perfect. Yes, it does. And also, Sandeep, thanks you. And so I would say that it was, you were answering his question.
Okay, good.
So I think no more questions. So I think we can move on whenever you want.
I've just discovered how to find the chat. I'm sharing. That's okay. I'll know for next time. Good. Right. So now we're back in R, and we are ready to. We've defined the any deployments that we want to discard or discount from distance, and discount the distance information for. We are ready to make an REM estimate. So I'm going to create an object called est. And I'm going to assign that, and I'm going to assign an REM density estimate to it by running REM estimate. And all I need to do is pass in my data package. Okay. So if I run that, we'll see similarly to when I, oh, hang on, what am I doing? That's odd. For some reason, it was running the last line. Occasionally, R does odd things like that. Let's rerun that. Ah, okay, right. I've just remembered why it's doing that. No, that's absolutely logical. By default, if I run this very limited version, or the default version, there are various other arguments that I could give to this function. But if I run this, it automatically runs. It forces me to run a deployment calibration model check. So that makes sure that you're not just running this without thinking about the calibration models, and making sure that you're using only good ones. Of course, it's a pain if you want to run this for multiple species on the same package, for example. You don't want to have to do this every time. It doesn't matter which species. If a deployment calibration is bad, then it's bad for all species. So what you want to do is say that I'm going to run this for my package 2, which just above here is the result of a deployment check, deployment model check. So I've already flagged which deployments I want to use, but I want to tell it that I've already done it. This package doesn't need to be checked because I've already done it. So let's just remind me, always need reminding, what the arguments for this function are. I should say, actually, that if you want to get full help on a function, you can run this. So if you just write the function name preceded by a question mark. Oh, hang on, sorry, I'm in an interactive mode. I just need to get out of that. So if I run that, I will get help on this. So I get a list of all the arguments. So this one here, jet deployments, by default is true. So that means that if I don't change that argument, I will have to run the deployment check first before it will do any density estimation analysis. I can tell it which species I want to analyze, or I can do an interactive selection. And then I'll talk more about these other arguments later. But it gives you a bit more verbal information about these these arguments. It describes what they are, how to use them, what comes out. So the other way that you can just get a quick reminder is to run args and then get in the console down here. Say, oh yeah, I remember now. The argument is called check deployments, and I want to change that value. So I could just write false here because that is the second argument. But generally, it's probably a good idea to write out the argument name as check deployments is false, so I don't need to rerun the deployment checking. Just because that makes the whole thing a bit more legible when you come back to it later. So if I run that now, I will get this species selection dialog down in the console again. So nothing's happening yet because it's waiting for me to tell it which species I want to get a density estimate for. So if I put my cursor in the console, say let's do fox, vulpes. I want to select that one, so 2 and enter. And you can see it's doing stuff. So it's reminding me that for the species, I've selected that species. Now it's telling me that it's analyzing that species. And then it's telling me that it's fitting a radius model. So remember, these are the parameters of the REM model overall. We want to estimate. It's fitting the angle model, then it's fitting the speed model. Finally, it's fitting the activity model. This usually is the longest one. It's doing some intensive resampling of data in order to do that. So if you run that, it can take quite a long time if you have a lot of observations. So just to be aware of that, but just so you don't think that the program has stalled and hung up. You have this progress bar just to reassure you that something is happening, and we'll get there in the end. Then finally it calculates density, and then it's done, and we have a result. So now we have this object called est. Again, we can see that that's appeared in the environment. You can see that it's a list of 7 things. So if I environment, I have a look at what those are. So it records what species it was. It was vulpes. It's got some data. So this is the trap rate data. And then it's got a table of estimates, which I'll have a look at in more detail in a moment. And then it's got some of the underlying models. So it's got a speed model. It's got an activity model. It's got a radius model and an angle model. If I want to access any of those individually, if I type the name of the object and then a $, I can access each of those components, and we can actually see into them a little bit. So the data looks like this. So this is for each location. Oops. We've got the number of observations that there were of fox. We've got the effort, so that's the number of camera days. The unit of that happens to be days. May not necessarily be, but that's the default. It's crucial when we're doing REM that we know what the units are. So those are recorded. Estimates I'll come back to. This is where we get to what we really want to know, the species I showed you earlier. So these are the speed, activity, radius, and angle models are all more complex data objects that contain all the information for the models that were fitted to data on using the distance information and the time of day information in order to understand the values on those parameters. So what's the first thing we want to do is a little bit of model checking. So as we were checking the calibration, the deployment calibration models, we want to look at some of those underlying models to just double check that they make sense. So the easiest way to do that is visually using plots. So we want to plot, for example, radius model. So if we plot that, one thing we want to change here is that we want to plot the PDF, so the probability density function. By default, if we just plot that, it'll give us the probability of detection, which is also interesting. But if we want to look at the raw data distribution, we need to set PDF to true. So this isn't very informative because this is a very small test set of data, toy data set. You should hopefully see more data-rich environments. So if you've got 20, I suggested ideally 200 odd at least observations digitized. So you should see much richer distribution of those rather than just a handful of observations as here. But what you should see is an initial increase away from the camera as just as a function of the shape of the detection zone. If detection is perfect, you would just see more and more animals as you go further out because the sampled area increases. But then at some point, because detectability declines, you start to miss animals and you see a decline. So you should see a curve that starts from the bottom of the graph, goes rapidly up and then decays away again, with the data distribution fitting reasonably under that. You might see that there are some outliers, so I wouldn't want to say that that observation at 11 meters is definitely an outlier in this, given the small size of the data set. But if you have, a lot of observations within a reasonable distance, 6-8 meters maybe, but then a few observations out to maybe 10-15 meters beyond that are seem to be really outlying from the rest of the data, you might want to truncate those. And I'll talk about how you do that in a moment. If you want to look at the fit for the angle model, similar, but we don't need to change anything else in that. So it's simply plot that model. This is the sort of distribution you might see. Again, it's very data poor, but I think when I first started exploring these models, I tended to see the camera model that I was using at the time, this sort of pattern with a decline away from the center line. So in this case, the distance is not at radial distance from the camera, it's angle, so angle in radians. So this is going out to the edge of the camera about 20 degrees or so in this case. Is the radian equivalent. So that's saying that things are a little less detectable towards the edge. In practice, what I'm seeing with a lot of models now is that you tend to get rather fewer observations in the center and then a peak of observations at the edge. In that case, you'll just get a straight line right across with the effective detection angle being the maximum distance. That's fine. The model will look like it fits poorly, which it does in principle, but it doesn't matter. It's giving us the right result that we effectively, there's no serious decline in detectability towards the edge of the field of view. And I think that's just a function of perhaps better sensors or different configurations that make it maybe with the sensor set outside the camera's field of view, so that you tend to pick animals up very quickly. Maybe more sensitive triggers where the camera reacts more quickly, that sort of thing. So that sort of apparent lack of model fit is not a problem in the case of angle. You might want to look at the distribution of speeds. So again, this is our speeds while active. So this is using the tracking of individual observations as the animal passes the camera. We get multiple positions. From that, we calculate the speed whilst that active animal is passing. Oops, sorry, I forgot. This is a slightly different function we want to use. So this is like the base function hist to give a frequency histogram. So we want to look at the frequency histogram of speeds. And by default, it gives us the log of speed. So those are not raw speeds. That's why you have minuses. Those are speeds of between 0 and 1 meters per second. So the slower speeds still. You might want to, doing this in the console, doing what I said not to do. Let's plot this in the our script file so that it can be preserved. We might want to look at that on a untransformed scale. So we can do that by switching off the log argument. And then we get the raw speeds. So these are the distribution of raw speeds. So most of them are less than 1 meter per second. There's a few outliers up here. When you have more data for these, what you'll find is that you have they're hugely right skewed. A few very high speeds, and then lots of very low ones. So if you that's the reason why the default is to look at the log scale, because usually we find that it's roughly a log normal distribution. You can see more easily what's going on with that distribution. So there isn't a model fit to see there. The default here is to estimate the average speed using a non-parametric method. So there's no need to judge model fit, but it could be useful just to see whether the distribution of speeds looks reasonable. And then finally, we might want to have a look at the activity model. So this is based on the time of day at which each observation appears. So if we plot that, we can see the daily cycle here from midnight to midnight, and the distribution. So the bars here are the distribution of when the records occur. So these are exclusively nighttime records, as it happens. In this small data set, foxes are pretty nocturnal in this area. And then the wobbly lines are the estimated activity level based on those data. And the dotted line, that's the solid line. The dotted lines are the confidence interval on that line. So again, pretty wide confidence interval here because we have so few data, but you should see a much nicer pattern, tighter confidence intervals, and a good correspondence between the model and the data. So that's a way of just visualizing, checking that everything kind of makes sense. You might raise some concerns there, various things that can potentially be of concern. So if the models are not fitting well, it might be an issue. If you're ready, then you're happy with all of your underlying models, we can look at the density results. So what to do is to look at our estimates. So if I run that, we can inspect them in the console. So we get a table here of all our estimates. So our estimated effective detection radius from this model here is about 4.5 meters. So based on analyzing this fitted detection curve, we can estimate that. You can see the units here, so 4.6 meters. We also get the standard error. We get the coefficient of variation, CV for short, which is the standard error as a portion of the estimate. So this is roughly 10%, just a little bit less, 0.09. And the confidence interval, the lower and upper 95% confidence intervals for those, and the sample size, so we can see how many data points each of these estimates was based on. And they can vary. So the radius was slightly less because there was an extreme outlier that was truncated by default. That's a standard thing to do in distance sampling practice. So that's not necessarily something to worry about. We had fewer speed observations simply because some of the digitized observations were only a single point. We didn't get a track of movement. The animal just appeared once and was gone. But that again is fine. That's not a problem. So our estimated active speed is converted here to kilometers per hour. So 1.5 kilometers per hour seems about reasonable. Foxes generally move around fairly actively when they are active, moving fairly fast. Activity level is based on this fitted curve here. So we've got, basically it's the area under this fitted model curve as a proportion of the total possible area under the peak activity here. So that's about 25% in this case. So that's indicating about an activity level of 25%, 26. That's suggesting they're spending about 25% of their time actually active and available to cameras. So if we multiply this speed while active by the activity level, we come out at an overall daily distance traveled. That's the overall speed, which in this case is just a little under 10 kilometers per day. So we can kind of sense check whether those feel about right. This is actually within the, even though this is a tiny data set, and I wouldn't want to rely on it for a density estimate. That sort of daily distance traveled is within the sort of range that we might expect from carnivore of that size. So we're already getting reasonable results there, I think. And we have almost finally, we have the trap rate. And the sample size there is the number of locations. So remember we had 3 locations, so got that. And then we have finally, REM density estimate. So putting all of these bits of information together, what are the implications for our estimated speed? We get an estimate of 11 animals per square kilometer, standard error of 6, which is a pretty high CV. Problem is that when we're putting all of these estimates together, the standard errors kind of compound on top of one another. So see that the coefficient of variation is a little bit more than that of the highest coefficient of variation in the component parameters. So usually our highest coefficient of variation will be in trap rate. I think as a function of this small sample size, that's not the case, but you usually find that's the case. And that is a function of your survey design. Usually it's partly a function of how the animals are moving space. So if all of your observations are concentrated on 1 or 2 deployments, then that can give you very high coefficient of variation. But you can ameliorate to that to some extent by having more locations. So that's why there's a recommendation on a minimum number of locations to sample Yeah, so that's it. You have your estimate. You can start extracting that and reporting it, putting that into this information into the any published papers, obviously, and also the EOW reporting system. That is about it, really. But I just want to say a little bit about slightly more flexible ways of using this. So when I fitted the REM density estimate, I just used this minimal set of arguments, but you can construct things more flexibly if you need to. So you can fit your models separately. So there are a suite of functions for fitting the models separately. So if I do fit underscore, we'll see we've got fit act model. So we can fit an act model independently. We can fit a detection model independently for either radius or angle. And we can fit a speed model to fit estimate the effective speed while active, the average speed while active separately, and then we can supply those to the REM estimate separately. So when I use the default settings without and allow the models to be chosen internally, there are some default assumptions made about how we want to truncate data, for example. But if you want to take more control of that, so say that I wanted to have go back to this, I wanted to truncate my distance distribution, let's say 6, instead of going out further beyond that, I could fit a detection model. So I want to say that my radius, this is a standard R formula. So the tilde, the squiggle here, says that I want my radius to be a function of something. So actually, I don't want it to be related to anything. I could do a model here where radius was a function of, say, body mass or time of day. So it might change day or night, for example. We can do more sensitive models like that. That's a more advanced level of modeling, which I'm not going to touch on now, but just to make you aware that that is something that can happen potentially if you want to refine your estimates. But at the moment, I'm just going to fit a model where I just want a single estimate of effective detection radius, but I want to change the some aspects of that. So the first argument is how I want the model structured. The second is the data that I want to use. So I'm going to use my package 2 again. And then there are a range of arguments that I can use to modify the model. So one is that I want to change the truncation. So I want to bring that into 6 meters. So if I fit that, again, actually, another thing that you can change. So if you're running lots of these, I could create an object, an R object called SPA for short. Say that I'm doing a whole set of bespoke models for Fox. So I want that to be Volpes. So now I can add an argument that says I want a species to be that. So if I create that species variable and I run that, I don't have to choose this time. It'll just fit that model. Oh, forgot to assign that. So it just spat out the results there. You can see that my effective detection radius is a little lower this time, 3.6. But now I've assigned that to this object. I can reuse that. Now I want to refit my density estimate. Again, using package 2. Now I can again define my species so I don't have to select. Not forgetting that I want to check deployments is false. So I want to switch that off because I've already done that with this data package. Species is good, and activity model. So let's just make this a little bit more legible by putting the arguments. Each argument is separated by a comma. Just to note, I should have noted that at the beginning, but just to make that a bit more legible, I'll put them on different lines. So remember to switch off checking deployments. Remember to, or we can define species rather than choosing interactively. And then sorry. Well, I've just done a bespoke radius model with a different truncation. Let's have a look at what that looks like first. So now you can see that it's, oops. Yeah, so we get this sort of pattern. So that's carried out the truncation as we asked. Now we want to, rather than allowing the model to be, the radius model to be fitted by default within the REM estimate, we're going to override that and give it our bespoke model. So it says it's fitting radius model, but actually it didn't do that. It just ingested the model that I gave it. Just rerunning everything else. And then the difference that it makes. So now we've got this new radius 3.6, that's the estimated effective detection radius, and it makes a small difference to the density, but not much. One thing I would caution is not to spend too long, trying lots of different models and then getting lost in lots of different possibilities and wondering what the right answer is. I think you should only start using these more flexible model fitting processes or options if it really looks like there are problems with the data that you need to fix, and there's a good reason why you expect to get poor results with the default version. But the majority of the time, I think you should just be able to use the default settings. It's just good to be aware that these more advanced options are available if you need them. I think that's me. I hope it was all clear.
Thank you very much, Marcus. It was extremely clear, I think. And there's one question from Antonio in the chat.
Hang on a second. Prove that it's right. It's supposed to use both the initial and the final sequence. But this is a really good question. At the moment, the Agouti setup is doesn't make it easy to do that. I think this slightly hesitate to suggest it, but one thing you could do is just digitize holes from both the initial and the final. So that will give you a model that is a kind of ensemble of data from both of those. So it's if there is a little bit of camera movement, it will give you an answer for distance predictions somewhere in between what was the case at the beginning and what it was at the end. If you have a lot of camera movement, that's not ideal. Ideally, you want to separate deployments. So one thing you could do, this is a bit labor intensive, but identify the point at which the camera moved and separate those into two deployments. So create a deployment for with the initial calibration, pull images for all of the animals up to the point at which the camera moved, and then have a second deployment with the calibration images at the end for the rest of the deployment. If you have multiple movements, that obviously you'll have stuff in the middle where that won't work. The best thing may be just to ignore those, not digitize any animals from those, but that we don't have a very good workflow for identifying those at the moment, I'm afraid. So we just have to find ways of working in that way. But that's the principle. There's a couple of options there. Hope that makes sense.
Anyway, correct me if I'm wrong, Marcus, but in case the camera didn't move, and if you just calibrate, digitize both initial and final calibrations, they're both going to be used for the
Yes.
model.
They will be both used, and that's fine. That just adds more data to your calibration model, which is good.
So yes, if the camera is not moved, you don't have to choose one or the other. You can digitize them both, and all the information is gonna be
correct.
Used.
Yeah. Jorge's question. In and out sequence. Do we need to do a new? Yeah. So if the animal has left the field of view, then and you don't know where it's gone, you haven't tracked it, it might be just out of view, or may have done a big circuit somewhere. You should not treat that as the same observation. When if it comes back and you want to include that, then you should create a new observation and a new track.
Okay, great. Does anyone else have other questions? I would like to remark that, okay, Sandeep.
Rule of thumb, minimum number of camera tracking points. So the minimum number of deployments. Yes. So my ideal suggestion would be 50 or more, but I think that probably is more than I can't remember what the recommendation is for EOW at the moment. It's less than that, isn't it?
Yeah, the EOW, I mean, the recommendation of the EOW is a minimum of 36.
Yeah.
But we also specify that there are evidences saying that, especially for species that have clustered behavior, so that often is for wild boar, a higher number is highly recommended for the what Marcus was explaining earlier about the CV of the trapping rate, which risks to be very high in case we don't have a higher number of cameras. So ideally, yes, as Marcus said, we suggest to have about that number, so 50 or even 60 if possible, but in that can be split in more sessions. But yes, the minimum number we recommend not to get below is 36.
Can you clarify your question, Nuno? Not sure what you're asking. What about independent evidence?
While waiting for Nuno to give more information about his question, I would like to remind that the GitHub page of Marcus, the one he has been suggesting earlier on, is extremely detailed and has a lot of information and examples about basically everything that he has been explaining so far. So that's also something you might want to have a look at in case you have some doubts that you're gonna have some doubts in the following weeks or so. And as said, of course, the recordings of this course are going to be shared, so you can have a look back at them in case any doubts are going to arise in future.
And I've just put the address for the GitHub site in the chat. Also, just to remind you, when you first enter that site, it doesn't look very helpful. You've got a lot of meaningless information, but you just scroll down a little and you get to the tutorial section where it steps you through the analyses. So use that to as your reference point. Oh, hang on, I'm not sharing. There we go. Yeah. Share. So when you first enter this site here, CamTrap Density GitHub site, it doesn't look very meaningful or helpful, but just scroll down a little bit and you get to the tutorial.
Perfect. So we got Nuno's question. Can you see it, Marcus?
Yeah, I'm just. Okay. What do you mean by treating the data in blocks? I mean, the basic idea is that each observation that you digitize should represent one individual animal passing through the detection zone. If you have a longer sequence of images where an individual enters and goes away for 30 seconds, but maybe that or a different individual comes back, then each of those occurrences of an individual entering and leaving the detection zone should be a different observation. If you're not digitizing it and you're just recording the number of individuals that came through, actually it's the number of those observations that you could have digitized. So you're looking at how many times did any animal of the same individual or not enter and leave the detection zone. I think that should be reasonably clear, but please shout if not, and we can discuss more. Yeah, you got it. Good.
So the trapping rate is not just computed based on the 2-minute sequences from before, but we are actually defining the independent events also in Agouti.
Yes,
correct?
That's a really important point to
Yeah.
keep in mind, actually, that when you're creating those observations in Agouti, that's absolutely crucial for defining your trapping rate ultimately.
Great, thanks.
Mm-hmm. Yeah, that's a good question from Antonio about whether so Jim suggested using where you have groups of animals for deer particularly. He indicated that you should just digitize one of the individuals in a sequence, which makes sense when you have plenty of data. You're not short of information. I think in practice, when it comes to species where you're really struggling for every bit of information, it can be reasonable to digitize every individual observation, even if they're within the same sequence. So if you want to do that for carnivore species, particularly where you don't have so many records, then that can make sense. Yeah.
If I can add about this, there's a specific function in Agouti that allows you to split one observation, because you might have one single observation with more individuals in it, because they are from the same class, so same species and same sex and age class. So you might have been annotating them in a single observation. Now there's a function that allows you to automatically split that observation into whatever number of individuals was recorded in that observation, and that is extremely useful in the digitizing process. So in case you want to track or digitize the movements of all the individuals, using that, you're going to have the single observations, which is what you need to digitize them all, because one observation can only record one single digitizing movement, one track. But as Marcus said, what Jim suggested was like for those situations where you have plenty of observations, and perhaps you have species like wild boars where you have females with dozens of piglets, and that might be a hell to track them all. But in case you need more trackings, then you can do them all. There's not a limit to it.